foundation course for mathematics, and let's continue with lesson 5 from the last video that we talk about the matrix. Today I'm gonna start with the computer graphic first. Can you think of the importance of matrix? Why we have to study matrix? So basically, one are an important use of the matrix is the use in the digital representations of an image. And how can we convert an image into the matrix? How it involves or how it relates between the image and the matrix. Basically, if you want to convert an image into a matrix, you can do that by dividing an image into a rectangular array. And that rectangular array is called the pixel. Have you ever heard about this word, pixel? I'm sure you guys have heard. So pixel is assigned a value that represents the color, which means it can represent the brightness, it can represent the darkness. Okay, depending on the number. For example, in a 256 level grayscale image, each pixel will be assigned the value between 0 and 255. So within this value 0 and 255, you will have different shades of the color from the white to black. And normally we represent the value of 0 as the white color, and we represent the black color by using the number 255. Okay? So in this figure number 2, as you can see, we have 8 level of grayscale, which means that we use the number from 0 to 7 that make 8 different level of the grayscale. And as you can see, 0 is the white color, whereas 7 is the black color. And the value between 0 and 7 is the variations or the shade, which is called grayscale. Alright? And in figure 3, you can see that in the figure A, you have the original image of the tree. But in the figure B, you can see that we divide that image into into a small number of rectangular region here, as you can see. And that is about 10 by 10 grid. Okay? So you have about 100 rectangular areas. Okay, right, and next in the figure 3C, as you can see, suppose we want to represent the X level of grayscale. We have to value or we have to range the value from 0 to 7. And as you can see here, there is no white color at all in the figure 3 of the matrix representations. Right, and that is how you can assign for the color of the grayscale starting from 0 to 8 and what you're gonna get as an image, like this. Okay, in the figure 3D, that is a digital image. After you separate the digital image into different rectangular regions, and then you assign the value for each of the regions. And then that is the converted from the matrix into different 8 level of grayscale. Right? That is one of the applications of the matrix. Okay? So next, we will talk about the inverse of matrix, and also if you are given with the equations, different equations, we can also be able to use matrix to solve the equations to find out the variable x, y, and z, and whatever. Okay, let's have a look together. Right, we will start with the inverse of the matrix, and then we will find the inverse of 2 by 2 matrix. If you have the matrix with the dimension of 2 by 2, how can we find its inverse? And the last one is the matrix equations. Okay, let's start with the first one, the inverse of a matrix. Right? But before we start with the inverse of the matrix, let me introduce you with this word first, identity matrix. So identity matrix basically it means you have the value of ones in the regions or in the directions that start from the top left to the bottom right. Basically, you have the value of ones in the main diagonal entry. and all other area it will be assigned as 0. For example, if you have like the I2, this number 2 here represent 2 by 2 matrix, okay, which means that you need A, B, C, and D that make 2 by 2 matrix. And it means if you want to represent I of 2, which means identity matrix, remember you have to have number 1s or the value of 1s along the diagonally axis, okay? Which means you're gonna have 1 here and 1 here. Therefore, the value of A will be equivalent to 1 and the value of D will be equivalent to 1. And where else will be assigned as the value of 0. So B should be equivalent to 0, C should be equivalent to 0 as well. And that is in along the diagonally, okay? How about if you have I of 4? So I of 4, this number 4 here is means 4 by 4, alright? And that 4 by 4 is A, B, C, D. Right, let me call A1, B1, C1, D1, A2, B2, C2, and D2, A3, B3, C3, and D3. And the last one is A4, B4, C4, and D4. Alright, so that's make 4 by 4 matrix. Okay, remember, number 1 will be along this, okay, around the diagonally dimensions. So that is 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 and 1, right? So that is in these directions. So this is how we identify the identity matrix. Okay, right here, this is I of 2 with 2 by 2 dimensions, I of 3 by 3 dimensions, and 4 by 4 dimensions. Okay, so the identity matrix is behave like the number 1. For example, if you multiply the identity matrix with the matrix itself, the result would be the matrix itself. Okay, so you multiply the matrix A with the identity matrix IN, you will end up with the same result, which is the A, the original matrix. Or if you multiply the identity matrix by any matrix, in this case it's B, you will end up the result with the B. Okay, so that's why the identity matrix is behave like number 1s. Remember, when you multiply 1s with any value, this one you get that value back. You multiply 7 by 1, you get 7 back. Or you multiply 1 by 0.5, you get that value, which is 0.5 back. Okay, that's it, the same as the identity matrix. Okay, right. The next example to verify that if you multiply the identity matrix with any matrix, you will end up the result with that matrix itself. For example, here you multiply the matrix I2, okay, with this, let's say, matrix A. And as you can see, after you multiply the two matrices, can you remember the rule for the two matrix multiplications? The columns in the first ones, okay, the number of columns in here must be equivalent to the number of rows in the second matrix. Okay, for example, here you have how many number of columns? You have 2, okay, in the first ones. And how many number of rows in the second matrix? 2 as well. So 2 is equivalent to 2. Therefore, you can be able to multiply these two matrices, I2 and A. Okay, and I hope you can remember how to multiply the two matrices. Okay, if you don't, just go back to the previous video or lessons, you will find how it works. Okay, and you can see that we finally ends up the result with the matrix A, right? Or even this one, you multiply matrix A with the I of 3, you will end up with the matrix A itself. Okay, as you can see. And I hope you can be able to find the multiplication between these two matrices. Okay. Next, what is the inverse of the matrix 2 by 2? we will start with the 2 by 2 first because that's the fundamental, and then we will increase the number of matrices like n by n. How can we do that in the final sections? Alright, if you want to find the inverse of the matrix 2 by 2, so basically the notations for the inverse of the matrix, we will use these notations, A and then raised to the power of -1, which means the inverse of matrix A. Okay, and in the definitions of the inverse 2 by 2 matrix, it is equivalent to 1 divided by A multiplied with D. Okay, and then you subtract that result by B multiplied by C. Okay, that is this one. And then you multiply that value with the another matrix. And that matrix is when you swap the position here. In this case, it used to be A, B, C, and D, right? But in this case, you will swap the position between A and D. So D here will be in these positions and A will be in the D positions. And B and C, keep it at the same positions. That is B, that is C. But you have to multiply that by -1. Okay, which means you need to take the negative of that value or multiply by -1 basically, right? So that is how you can find the inverse of the 2 by 2 matrix. And one point to note, the value of this one, AD minus BC, should not be equivalent to 0. So if it's 0, it means you cannot be able to find the inverse of that matrix. Okay? Right, and that quantity AD minus BC, okay, basically we call that one as the det or the determinant, right? And that is the determinant of the matrix 2 by 2, okay? Right, next, if you multiply the original matrix with its inverse, what you will end up with? Some might think, oh, it's original matrix. Some might think 1, or some might think it might be 0 or none, no answer, no solutions. Okay, let's look at this. If you multiply the original matrix with its inverse, you will end up with the identity matrix. Okay, you will end up with the identity matrix. But the dimensions of that identity matrix is also depends on your original matrix. For example, if your matrix A has the dimensions of maybe this one, okay, I write that, has the dimension of 2 by 2. Therefore, if you find the inverse of the matrix A and then you multiply it with the original matrix A, your result will be 1, 0, 0, and 1. This one, the matrix 2 by 2. Okay, when you have the identity of 2, this one. Right, that is also another property or the identity matrix. Alright, let's look at this example and then we will verify whether that property is true or not. But first, let us find the inverse of the matrix A first. Remember, if you want to find the inverse of the matrix A, you have to find the det first, okay, or the determinant. Right. And this is what we call the det or the determinant. Okay, it comes from A multiplied by D, that is 4 multiplied by 3, minus B multiplied by C, or 5 multiplied by 2. Right? And then that will be multiplied by another matrix. And that matrix is when you swap the position between A and D. So as you can see, 4 used to be here, but now it's located at the D position. And number 3 used to be in this position, but now it's in the A position or in the number 4 position. But 5 and 2 here remain the same, okay? But the only thing that difference is you multiply that 5 by -1, you multiply that 2 by -1, and that's why it's become -5 and -2. Alright? And after that, you can find the result, okay, of the det. So the determinant, the result of the determinant here is 2. 4 multiplied by 3 minus 5 multiplied by 10. Okay, 12 minus 10 is become 2. And then this one is also the property of the matrix. Alright, if you could remember from the last video that we talked about the matrix multiply with any scalar number. Okay, remember how to do that? This number has to multiply with every value inside the matrix. That is the rule for the multiplication between the matrix and the scalar number. Okay, so if you multiply 1 by 2 by 3, you will get 3 by 2, right? If you multiply minus 5 here by 1 by 2, you will get minus 5 by 2. And of course, that becomes minus 1, and that becomes 2, okay? So you multiply the scalar number with every value inside the matrix, right? And that's it, the inverse of the matrix A, okay? So we are done with that. And next, we will verify whether after you multiply the original A matrix with this inverse of A, it will be equivalent to the multiplication with the inverse of the matrix first and then followed by the original matrix. And whether the result will equivalent to the identity matrix of 2. Okay, let's see together. Right, let's start with A multiplied with the inverse of the matrix A together. Like this is an A, this is the inverse of an A. Again, the two matrices multiply together, making sure that the number of columns in here, okay, must be equivalent to the number of rows in here. But in this case, they are equivalent, therefore you can perform the next step of two multiplications between the two matrices. Okay, right. And after that, you will see that we'll end up with the identity matrix. Okay, that's it, the I of 2, right? And next, how about if we start with the inverse of the A first and then followed by the original matrix A? What would be the result for that? Okay, again, we got the same result, which is the I of 2. Okay, but if you multiply the matrix A first followed by B, and then the next one you start with B first followed by A. Remember from the last video we have verified that the matrix here, okay, the multiplication between these two matrices, if you swap the positions, the value are not always the same, right? You have to double check. Okay, the value are not the same. Go back to the previous video for that. Okay, we have already verified for this case. But in this case, A multiplied with the inverse of the A is equivalent to the A inverse first, and then followed by the multiplication by the original one. And that will end up with the I of the end. Okay? Okay, good. Next, how about the matrix equations? Another useful or the matrix apart from assign the value of the pixel for the digital image, we can also use the matrix to solve this kind of the linear system as well, right? Suppose you have 3 different equations here, 1, 2, and 3, and then we have 3 different equations and 3 different variables. That makes sense enough to find the value of these 3 variables. But if you take that step, it might take time, okay? It might take time. How about if you use the matrix equations to solve for the value of x, y, and z? You will save a lot of time, and the result will be the same as you perform the original way. So let's see how we can do that. Okay, in this case, you have to first translate each of the 3 equations into the form of the matrix equation first. And what is the matrix equations? Right here, as you can see, this one, okay, let me call it as the matrix A, okay? In the matrix A, we will take the coefficients that is associated with the variable x, variable of y, and the z out. Okay, so in the first one here, you have 1, that is 1 for the x. You have -2, that is -2 for the y's. You have -4, and that is -4 for the z. Okay, so basically these columns represent for the coefficients of the x. These columns represent for the coefficients of the y's, and the last one represent for the coefficients of the z. And then this one is the first of the the first equations, and that one is come from the second equations, and that one is come from the last equations. Okay, so now we are done with the A, right? And next, that value will be multiplied by the X matrix. And this capital X matrix here represent for the variable, okay, which is X, Y, and Z. Why we have to write in one single columns and 3 different rows? It's because if you multiply that, and that by this and this and this number, you will end up with the same as the original equations. Okay, so in this case, if you multiply this x by 1, you will get x. You multiply this y by -2, you will get -2y. You multiply z by -4, you will get that one back. And the same as the second one and the third one. Okay, and make that equivalent to the value or to the number on the right hand side of the equations. And then we can just write this value as a single column, okay, and we represent that as matrix B. So now we have 3 different matrices. Okay, we have 3 different matrices. So in this case, we call it as the matrix equations. So basically, the matrix equation is AX equivalent to B, where A is from the coefficients or that of each of the 3 variables. X is the capital X, I have to say the capital X is basically the variable that you have in the equations, and that B is the value or the number that located on the right hand side of the equations. Okay, good. Next. So now we can identify into 3 different matrices, the A, the capital X, and the B. Alright? And we can express the matrix equations as in this way, AX equivalent to B. Okay, AX equivalent to B. So if you try to multiply matrix A and matrix X, you will end up with the original equations. Okay. Right, but our goal is to find the matrix X. Okay, our goal is to find the matrix X. Remember, the matrix X here is basically X, Y, and Z. So we have to find the value here for the X, the value here for the Y, and the value here for the Z. That is our goal. So it's just like the number. Remember, if you have like 5x equivalent to 10, if you want to find or if you want to look for the value of x here, you have to move this number 5 to another side of the expressions. Basically, you divide that by 5. Okay? And then you will get the value. Just like the same as the matrix. So when you move this matrix A to another side of the equations, you will have to, basically you have to divide, right? If it is a number like in this case. But for the matrix terms, you have to change it into its inverse. Okay, you have to change it into its inverse. That is the inverse of the matrix A. Therefore, to find the value of the x, y, and z, you have to find the inverse of the A matrix first, and then you multiply that by another matrix B. Okay. Alright, let's look at this together. So in this example number 4, I first ask you to write the system of equations and the matrix equations. Remember, as a matrix equation, which means you have to identify the A, the X, and the B. Okay, of that ones. And then the second part, in part B, you have to solve the value of x and y, because in this example you only got 2 different variables and 2 equations. Okay, let's start with the first one. The first one, to express the matrix in terms of the matrix equations. So that is the case. You have A, X, and B. Alright. So the A here is the coefficients, and X here is the variable, and B here is the solutions or the result. Okay, so that is how you can explain it in terms of matrix equations. Right, now we are done with the matrix equation in part A, and next we'll move on to find the value of x, y. But remember, before we find that, we have to look for the inverse of the matrix A. Why is that? If you want to look for the x, okay, you have to multiply that. You have to multiply that by the inverse of the A. Okay, so that would be this one, right? Therefore, next step you have to find the inverse of the matrix A. Right? So this is the matrix A, and then I write in this notation to represent its inverse. Right? I hope you can be able to find the inverse of matrix 2 by 2. Remember, 1 divided by the depth. Okay, the depth is come from multiplication between these two minus with the multiplication between that two. And then multiply with another matrix. And that matrix is when you swap the position between 2 and 6 here. And the position of 3 and minus 5 remain the same. Okay, but you have to multiply that by minus 1, and that become minus 3, and that should be plus 5. Okay, and then you find the result or the inverse. Right, and next we have to move the matrix A to another side of the equations, and that becomes the inverse of the matrix A, and here is the inverse of the matrix A. And X, the capital X here, remember, it represents a single columns of the variable, which is X and Y. And B here represents the solutions of the equations. So now you have to multiply the between the inverse of the matrix A and the matrix B. Okay, and the result here is 30 and 9. All right. Therefore, we can say that X is equivalent to 30, whereas Y is equivalent to 9. So that is the result. So if you still are not sure whether your result is correct or not, you can use the original way to find. Okay, you can use the original way to find two different variables with two different equations. All right. Next one's the determinant. We know how to find the determinant of the matrix 2 by 2. The depth of the matrix 2 by 2, okay, is equivalent to 1. Oh, sorry, not that one. Is equivalent to 1 divided by the depth. Sorry, that should be the inverse. All right, and that will be multiplied by the positions between the A and the D that already swapped, and B and C have been changed, but you multiply that by minus 1, multiply that by minus 1. All right, that is the inverse of the A. Okay, or the inverse of 2 by 2 matrix. And here is the depth. Okay, that is the depth of the matrix 2 by 2. And how you can find that? Remember, it's A multiplied by D minus D multiplied by C. So this is the value of the depth of the matrix 2 by 2. But how about if you have more than 2 by 2 matrix? How can we do that? We cannot use the same method to find. Let's have a look together. Right, here is the objective of these sections. We have already done the determinants of the matrix 2 by 2, and next we will talk about the determinants of the matrix n by n. Okay, and also the row and the column transformations. Okay, so let's start with the determinants of the matrix 2 by 2 first. Remember, if your original matrix is given in this, and then your depth is equivalent to the value or the multiplication between A and D minus with the multiplication between B and C. Okay, and that is the depth of matrix 2 by 2. Easy, right? Have a look at this example together. right? So the that here is when you multiply 6 and 3, and then you subtract that by the multiplication between minus 3 and 2, and the result is 24. And how about if you have matrix 3 by 3, 4 by 4, and 5 by 5? How can you do that? Okay, we have a single rule. Okay, right? You first have to understand the checkerboard pattern first. Okay, so the checkerboard pattern is means along the diagonally axis you have the positive number. All right, in this way. And also from the top line to the down left, you have the positive value. Other area or the other regions will be assigned with the negative value. Okay, right? That is the first rule. Understand the checkerboard pattern first. Or if you have that is 3 by 3, but if you have like 4 by 4. The checkerboard patterns remain the same. That would be this case. Okay, minus, minus, and that should be plus. That should be minus, and that should be I think plus. Okay, so along this way you have plus, and along this way you have plus. So that should be plus. That should be plus. That minus, 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 minus here. All right. So that's it. The 4 by 4 checkerboard pattern. Okay, next step. When you find the determinant, you can choose to fix any row. Okay, you can choose to fix any row. For example, in these definitions, we try to fix the first row, and then you vary the list. Okay, or if you try to fix the second row and you vary the list, the result should be the same. Okay, so let's see together. We call that way as the expanding determinant. You can expand the determinant by choosing any row to fix. Okay, but the result will be the same. For example, let's take a look at this. So if I ask you to find the determinant of this matrix A, 3 by 3, okay? And then I first choose to fix the first row, okay? I first choose to fix the first row, and I have to vary the rest here, right? Then this step here is quite easy. Remember the checkerboard patterns, you have positive, okay? You have positive along these directions and along these directions, okay? Which means that if the number in the row that you have fixed has been crossed out, then that value will need to be multiplied by +1. But the rest will be multiplied by -1. Okay, so I start with number 2 first. And number 2 here, the first row, I wish you to expand the determinants by fixing the first row. So I fix number 2. I fix number 3, and I fix -1. Right? And then the number that I choose, it had to be multiplied by -1 and +1, depending on whether it has been crossed out around the checkerboard patterns or not. In this case, the number 2 and -1 has been crossed out. If it has been crossed out, I have to multiply that by +1. But if it haven't crossed out, I have to multiply that by -1. Like number 3 here, it haven't been crossed out, therefore it had to be multiplied by -1. And -1 here, okay, it has been crossed out as well because it's wrong the directions of the checkerboard patterns. Therefore, I have to multiply that by +1. Okay? Right, that's it, the first step. And then next step, let's start with number 2 first. So number 2 here is right here, right? So number 2 here is on the first row, then you close the first row. And number 2 is also in the first column as well, so you close the second column. And then you multiply this number 2 here with the rate of the number that haven't been crossed out. Or in other words, you have to multiply this number 2 with the matrix that is not located in the same row and in the same columns as that value. Okay, so in this case, you have to multiply that number 2 by 2, 4, 5, and 6. Okay, the matrix 2, 4, 5, and 6. Alright. And then this one, you have to add up with that number 3. But remember that value 3 has to be multiplied by -1 because it hasn't been crossed out. Then it will be multiplied with the value that are not located in the same row and in the same columns. So in this case, it is 0, -2, 4, and 6. 0, 4, -2, and 6. Oh, I have already shown you that. Alright? And then if we have to add up with the last one. Last value, which is this -1, you cross out and you cross out that. Therefore, it should be this full number that is 0, 2, -2, and then 5. Alright, so that is how you can find the determinants by in this case you should to fix the first row. Okay, you should to fix the first row, and that is how you can find. Right, and then in this and this, okay, should be easy for you. So basically, each of these 3 we call it as the depth of 2. Okay, the depth of matrix 2 by 2. Right, you can be able to find that. Multiply between 2 and 6 minus the multiplication between 5 and 4, and this one as well. Okay, right. And here is the result. You find the depth of the matrix 2 by 2 first. You find the depth of the matrix 2 by 2. You find the depth first. And then you multiply that with these 2 numbers, this number 3 and this -1. And here is the result. You got -44. Okay, so that is when you expand the determinants by fixing the first row. And next example, you can also try to fit the other row. For example, in the part A, you can try to fix the second row, or you can try to fix the third row, and let's see the result. Okay, let's start with the part A, when we fix the second row. So when you fix the second row, remember, along the diagonal exit here, okay, if the number has been crossed out, then you have to multiply that value by the +1. Like in this case, number 2 has been crossed out, then you multiply that number 2 by 1, then you got +2. And 0 and 4 haven't been crossed out along the checkerboard patterns. Therefore, this value 0 had to be multiplied by -1. And this number 4 here had to be multiplied by -1. And that's why it becomes -4 here. Okay? Right, and next we start with 0. So we cross the row of 0. We cross the columns of 0. And then as you can see, we have left with 3, -1, 5, and then 6. And then you just rewrite that 4 number again. Okay, so in this way you have 3, -1, 5, and 6. And after that, you can find the depth of this one. Just like the number 2 here, you close these columns, you cut this row, and you have left with this, and this. So that is 2 -1, and that's -2, and that is 6. And then you find the determinants of that. Alright, and the same as number 4. And let's see the result together. It should be equivalent to -44. Okay, we got minus 44, which is the same as in part 3, in example 2, right? When we fix the first row. Okay, the last ones. How about not just the row that you can fix, you can also try to fix the column as well. For example, in this 3B, we fix the third column. So if you fix the third column, what is the first step you have to do? Again, you have to cross out, okay? And let's see if the number has been crossed out or not. If that is the case, then this minus 1 had to be multiplied by plus 1. This value of 6 had been crossed out as well. You have to multiply that 6 by 1. But this number 4 haven't been crossed out, then you have to multiply that by minus 1. And that's why you got minus 1, that's why you got minus 4 here, and that's why you got 6 here. Okay, and again, the same as the previous example. Number 1 here, you cross the columns of the value of minus 1. You cross the row where the minus 1 has been located at. And then these are the remaining value that haven't been crossed out. In other words, it means these 4 number here is not located in the same columns and the same row as that value minus 1. Okay, and then you find the date here. Again, number 4. So you cross the row of number 4, you cross the columns of number 4, and you have left with these 4. That is 2 and 3, and that is minus 2 and 5. Okay, and also the same as number 6, you cross this row, you cross these columns, and these 4 here, 2, 3, 0, and 2, right? That have been crossed out. Therefore, you find the date for the 3 of these, and then you multiply the result and then add up the result. And the value should be minus 44, because if you try to explain which row or which columns, the number should be the same, okay? And that is how you can find the determinant of end by end matrix. Okay, so you can double check your result by expanding different row or different column, and then you check the result. If they are the same, means that your result is correct. Right? Okay. Right. So that is the same value. Okay. So that the end of the lesson 5, and thank you for watching, and stay tuned for the new video from this channel. Goodbye.